Welcome to Calculus 1. Before I record section 4.3, I'm going to go back to 4.2 and I left out this application problem with the mean value theorem. So I'm going to go ahead and do it right here. Very interesting problem, actually. Two stationary patrol cars, equipped with a radar, that are 5 miles apart. So I got two patrol cars 5 miles apart. A car passes the first patrol car and clocked at 55 miles per hour. And then 4 minutes later, as the car passes the second patrol car, it was clocked at 50 miles per hour. Find the average velocity of the car at some time during the 4 minutes. Okay, what is the average velocity? And I think time got a lot to do with this. Okay, you get through 5 miles at 4 minutes. Okay, it's kind of fast. All right, so let's see how mean value theorem can kind of help us. First thing first, this 4 minutes, we need to convert it into minutes. I mean into hours, because everybody else is saying hours. So 4 minutes out of 60 minutes in an hour. They tell me 4 minutes is 1/15 hour. All right, I'm gonna let S of t to represent the distance traveled. I'm going to let S of t to be distance traveled by the car. So when the time is 0, okay, the distance must be 0 miles. So that's my starting point of the first patrol car. 4 minutes later, 1/15 hour, I will have traveled 5 miles. Okay, so our average velocity, alright, if I use the mean value theorem here, that will be S of 1/15 minus S of 0 over 1/15, the B minus the A. So if you really think about it, S of 15 is 5 miles. 5 minus 0 is 5 over 1/15. So that means the average velocity is actually 75 miles per hour. So what I tell this, if this position function, okay, is differentiable, we can apply the mean value theorem that the car have been traveling at 75 miles per hour, okay, during that sometime 4 minutes. Okay, that's very, very neat. capture the speed within a certain interval. All right. So I just want to show y'all an application using the mean value theorem. Alright, now let's take a look at the increase-decrease functions in the first derivative test. Okay, you can kind of see that a function that's increasing means what is going upward. A function decreasing means it's going downward. From where? From basically from its relative maximum or minimum. Okay. Or you could just look at it. It doesn't have to be necessarily be relative max or minimum. But whenever we see the graph kind of going up or going down, that's when we're talking about increase, decrease part of the function. But a little bit better way to word it is, a function is increasing as the x moves to the right, the graph moves up. The function is decreasing as the x moving to the right, its graph moves downward. Okay. So to test for the increasing decreasing function, okay, using derivative, let me move this up a little bit. Alright, if my function f is continuous on a closed interval from a to b and differentiable on the open interval a to b, if f prime of x is greater than 0, okay, then the f is increasing from a to b. If f prime of x is less than 0, that means the function is decreasing. If f prime of x is equal to 0, so that means from a to b, that means the f is constant, okay, on that interval. Alright, so if my derivative of the function is greater than 0 or less than 0, that will tell me whether my function is increasing or decreasing. Alright, so let's try the example right here real quick. Find the open interval on which a function is increase, decrease, or stay constant. So here's my function. So I need to take a derivative first, because all these guys are using f prime. So if I take a derivative, that will give me 3x squared minus, if I move this 2 down here, 2 in the bottom 2 cancel out, that will just be minus 3x. Alright, I'm going to find my critical point like I done before, set it equal to 0, go ahead and factor out the 3x as well, to give me x minus 1. So set each factor equal to 0, x equal to 0, x equal to 1. So these two numbers again are my critical numbers. Alright, so let's take a look at the intervals, okay, on which the function is increasing or decreasing. Let's check it out. To the left side of this critical number is 0, so that will be from negative infinity all the way to 0. Alright, I'm gonna use negative 1 to test. So f prime of negative 1. Okay, in this interval I'm gonna use the test value negative 1. If I plug in negative 1 into my f prime, I believe the answer will be 6, which we know is greater than 0. Alright, greater than 0 means f prime of x is greater than 0 means the function f is increasing. So this part is increasing. Between the two critical numbers, from 0 to 1, I'm going to use a half. So f prime of half, if I was plugging half in here, 3 times a half, half minus 1, times half minus 1, I think that's negative 3 over 4, which is less than 0. So that tells me my function is decreasing. To the right side of 1, the interval from 1 to infinity, I'm going to use positive 2. F prime of 2, 6, let me positive 6 again, greater than 0. So that part will be increasing. So my interval is increasing is negative infinity to 0, 1 to infinity. The part is decreasing is 0. So if I go from increase to decrease, decrease to increase, that tells me something's going on in between, which I will talk about that later on. Now, this example is real neat. Find the open interval on which the function is increasing or decreasing. Alright, a to the third power. If I just do the same thing as I done with the previous problem, alright, so this will, f prime will give me 3x squared. To find the critical value, I set it equal to 0. And as you can see, the critical value, x got to equal to 0. So, if I look at the interval to the left of my critical value, that will be from negative infinity to infinity. negative infinity to 0. And if I will substitute like a -1 in here, -1 squared times 3 would be +3, which is greater than 0. So that tell me, f prime, sorry. That tell me that part of the function is increasing to the right side of my critical number all the way to infinity. If I will pick +1, evaluate into my f prime, that was to give me another +3, which is also increasing. So what that tells me is this whole function is actually increasing, okay, on the entire domain, negative infinity. So we call this particular function, if it's all the way increased on the entire domain, we call that strictly monotonic. Okay, this function is strictly monotonic. Okay, just thought I will draw this up, kind of neat. It doesn't curve up or down, you just keep on going up the whole time. Alright, so let's see what the first derivative test is all about. Okay, after we see all the, which interval would be increasing or decreasing, it's not difficult to determine the relative extrema. The first derivative test, okay, says if f prime of x changes from negative to a positive at a c, okay, and the c of course is inside the interval, then f has a relative minimum at c comma fc. If my f prime of x changes from positive to a negative, okay, then my function has a relative maximum at c comma fc. If f prime of x is negative or positive on both sides of c, okay, if it's negative on both sides of c or positive on both sides of c, then f of c is neither relative minimum nor maximum. Okay, so if we go back to this problem, this one right here, okay, this is positive. Go from positive to negative. Okay, go from positive to negative. That tells me that there's a relative minimum, okay, which will be at my critical number 0. Go from negative to a positive. Excuse me, this is a relative maximum. Positive to negative, yeah, positive to negative is maximum. Negative to positive creates a relative minimum right here at my critical number. Alright, that's what first derivative test is telling us. Alright, so let's put the two problems together. Let's find the critical number f, then we can see on which interval the function is increasing, decreasing, so we can figure out the relative maximum minimum. So first thing first, let me take a derivative of my function so I can find my critical value. Alright, using the quotient rule, derivative of the top, which is 4x to the third, times the bottom, minus derivative of the bottom, which is 2x, times the top, x to the 4 plus 1. Whole thing over, derivative, the bottom squared. Alright, let me simplify this so I can set equal to 0. This is 4x to the 5th minus 2x to the 5th minus 2x, whole thing over, x to the 4th. So if I simplify this, if I subtract, that will give me 2x to the 5th minus 2x over x to the 4th. Factor out the 2x. So that'll give me x to the 4th minus 1 over x to the 4th. And the x can reduce out. So let's set it equal to 0. So let the x cancel out. So that will be 2 times x to the 4th minus 1 over x to the 3rd. Alright, this x to the 3rd cannot equal to 0. Okay. Alright, cross product, that will give me just 2 times x to the 4th minus 1 equal to 0. So if I factor this is a difference of square, that will give me x squared plus 1 times x squared minus 1 equal to 0. Factor again on this difference of square, it will be x squared plus 1 times x plus 1 x minus 1. Alright, so set each factor equal to 0. My answer x equal to -1, x equal to +1. If I set x squared plus 1 equal to 0 and solve for x, that's not a real number, so we're not worried about that. Alright, so I got two critical number here along with my x not equal to 0. Okay, so I can actually I'm going to use this x not equal to 0 again to help me to figure out the increase and decreasing part of the function. Alright, so my most left point is -1, so my interval -infinity to -1. Okay, f prime, I'm going to use -2 as a test value. If I plug in -2, okay, into my function, if I plug in -2 here, I think it will be negative. Alright, so if it's negative, that tells me that this part, that part of the, the function, the graph at this part is decreasing. Go from -1 to 0. Because I got x not equal to 0, I'm use that part too. F prime, let's choose -half. If I plug in -half, okay, into my function, I think it will be a positive. So that part of the function is increasing. Go from 0 to the next critical number, 0 to 1. Alright, let's use +half. Half, I think that would be negative, which is that part is decreasing. So this part is decreasing, this part is decreasing. From 1 to infinity, if I use +2 this time, excuse me, this is f prime. Alright, substitute 2 into my function, f prime. Right here, I can do it on this one too. I think that would be a positive. Alright, so that part is increasing. Alright, so here are the intervals that are increasing or decreasing. So whenever I go from decreasing to increasing part of the function, that will create a relative minimum. So that relative minimum got to be f of -1, because that's the critical number I'm using here. And if I plug in -1 back into my original function, okay, the y value got to equal to 2. From this part to that part, it's actually not in the domain, okay, and for the original function. It's actually not in the domain. So that part don't count. from decreasing to increasing again, there got to be another relative minimum. So if I substitute positive 1, since that's the critical number here, into the function, I think it will be a positive 2. So I actually end up having two relative minimum, negative 1, 2, and positive 1, 2. Okay. And if you will graph this function, you can kind of see, using the first derivative of the test, it can actually help me to identify my relative minimum or maximum. And I can also see, graphing, I can see which part is increasing and decreasing. Alright, that will conclude this video. Thank you for watching.